I will begin with a word of prayer once I get up here. Dear Father, we thank you for this day. I thank you for these students, this class. And thank you for your creation, that we can understand it, that you've given us minds to think about it, and that you've revealed your majesty in all that you do, Lord. Help us to glorify what we do and understand a little bit more about physics today, Lord. In my prayer, Lord Jesus. Amen. So, attendance. Here's the glorious attendance sheet. So if you can add a date and, that'd be awesome. All right, so I want to talk more about voltage, about finding. Sure, why not? I'm open. Just no future dates. Past dates are fine. Yeah. So the voltage function for a point charge, we've discussed that this is since it's the potential corresponding to the Coulomb field, it's sometimes called the Coulomb potential, right? And that's just V, which is equal to K, say Q, over script R, right? And so this would be the voltage at position vector R. And here, the deal is, we're talking about the charge Q. Why is it so hot in here? Good grief. So we're going to say it's at R1, and we're asking, I'm setting up the formula, mind you, for the voltage, say over here at position vector R, right? So we're asking, what's the voltage right there? V of R, it's equal to this. And that script R, as usual, is the vector which goes, as a vector, it goes from here to here, right? So the script R vector is R minus R1. Let's see if that makes sense. So if I add this plus that, the black vector plus the blue vector, I get the red vector. So that's a good sign that my formula is right. But you see, of course, in detail, this is actually what? KQ over, the length of the vector R minus R1, where I'm assuming that the charge Q is at R1. All right? So that's how to get the voltage for a point charge. Yeah? And here this presumes, this is subject what? The constraint that we want the voltage at, infinity to equal to 0, if you'll allow me that language. So very, very far away from the charge, we want the voltage to be 0. Now, it may or may not be possible to achieve this goal, right? Can we always make the voltage 0 very, very far away from where the charge is? Is that always possible? Well, the answer is no, because sometimes we consider idealizations where the charge just goes on and on, right? Like the plane charge, right? Think about this. The example last time we looked at the plane charge, a constant electric field, right? And in that, I wrote down the voltage. It was like minus E naught times X, or minus E naught times Y, or minus E naught times Z for electric fields respectively in the X direction, the Y direction, the Z direction, right? So what happens to those voltage functions if you think about it, right? So last time we had just to recap, we had V, V at R is equal to minus E naught X, or we had V of R equal to minus E naught Y. We had V of R equal to minus E naught Z, respectively, for the electric field E naught X hat, the electric field E naught Y hat, the electric field E naught Z hat, right? And it's pretty easy to take the gradient of my formulas and put a minus on it and see that you get those electric fields, right? That's a pretty easy integral, right? The integral of a constant is constant times x, right? But, and I talked about last time about where do we get a constant electric field, right? It's not just something that's a nice mathematical, yep. In a Gaussian surface. But a Gaussian surface is just a mathematical construction, so those are hard to find except in the addled brains of math professors, or perhaps physics professors. Where can we actually find a constant electric field in like a practical circuit case, you know? Like a real world example. Capacitors, right? Parallel plate capacitors. If you're close to the middle of the, you know, not towards the edges, but in the middle, you've got two charged plates, and so the electric field between those plates is essentially constant. So this is the voltage function that you'd find that would be appropriate like between capacitor plates. It's just linear with the distance. We're talking about the distance between, you know, perpendicular to the plane on which the charge is found. So my point to you guys is just, it's kind of a simple just point of order here, is we like to make the voltage zero at infinity, but we can't always do that. See, like these, if I go to, you know, a point very, very far away from the origin, x, y, or z is going to be huge, right? The voltage is not zero, far from it, right? So so here's like the general rule of order. We can only make the voltage zero at very, very far away if we have a local collection of charge. So like the charge can't be spread out to infinity. The charge has to be like, you know, within some finite locale. If that's the case, then you can make the voltage be zero very, very far away. All right, it's always possible, in fact. But you do need a local distribution of charge, and we don't always do that. Like we have 3 examples we look at in here which go on to infinity, right? The constant electric field that just goes on and on. That's an infinite example. There's another one. How about the infinite line charge, right? Think about that one. So, you know, example 1. Remember this? We had the electric field is lambda over 2 pi epsilon naught. Let's use s here for a difference. S hat over s, right? So here I'm talking about, we've got this lambda. Maybe, let me not draw it that way. Let me draw it, I mean, it's kind of more fun to draw the wire as if it's a point coming at you, right? Because that's where all the interesting geometry happens, right? So if I draw the line charge like it's coming out of the board at you, yeah? So there's my lambda. Let me just do one of these things. What does the electric field lines look like? They're radially out from that line, right? So if this was the charge distribution, like so, the electric fields are pointing perpendicular to that axis in all different directions, symmetrically so, right? That's what I mean by S hat. All right? What would the voltage be in this case? So what we're looking for. So by symmetry, we can say it should be minus dV ds s hat. So like this is minus the gradient of the voltage function, guys, because there can't be any dependence on the voltage except in that radial direction. And in fact, you could look in a sufficiently well-developed Calculus 3 book, and you find formulas for the gradient in cylindrical coordinates. And what you'll find when you do that is that the component of the gradient in the radial direction is just a derivative with respect to the radial coordinate times the unit vector in the radial direction. So like that's how it works out. More to the point, we need to solve. So let's see if we can solve it. Can you guys solve? dV ds equals to, say, minus lambda over 2 pi epsilon naught s. And we've already talked, I'm not like going to go through it again today, but we already know that that's the formula for the electric field because we apply the Gauss's law to a cylinder about the line, right? We went through this a couple times. So then what? You guys tell me, what's the voltage function here? So the lambda, the 2 pi, the epsilon naught, these are all constants, right? So here we go. The voltage at, let's say, S2 minus the voltage at, let's say, S1 would be equal to the integral from S1 to S2 of minus lambda over 2 pi epsilon naught ds over s, yeah? Can you, I hope you can do this integral. What do you got? We've got a minus lambda over 2 pi epsilon naught natural log the absolute value of S2 minus the natural log the absolute value of S1. And there's a parentheses here. Or if you like, we could say this. The voltage at S is equal to the voltage at some fixed radius S1 minus, well, let me say plus lambda over 2 pi epsilon, well, I don't know. I tell you, I can't think at this temperature. This is not helping. I just want to take a nap. Lambda over... It's not like this in other buildings. You guys take classes other buildings other than DeMoss. Like, there's actual air conditioning in those other buildings. Am I right? The new buildings have air conditioning, yeah? Yeah. I mean, I want to believe this building's been here for like 30 years. Why is there not air conditioning? Yeah. Oh. Hey, CFAW's coming up. It's going to get fixed before CFAW.
This weekend.
Yes.
They didn't fix the elevators last year, so I doubt it.
Well, a man can dream. All right, so natural log of... do you guys want me to leave the minus or not? I mean, should I leave the minus? I'm going to leave the minus. If I leave the minus here, I don't know. I'm sorry, I can't think. I really, seriously cannot think at this temperature. S divided by S1. Now, S and S... So, yeah. Yup. So anyway, this is how the voltage would work out for the line charge, something like this. It ends up involving the natural log. I guess if I put the... See, if I bring the minus in, it flips the denominator, so it makes it like S1 over S. And I guess as S goes to infinity, we get what? Oh. I mean, fine. Here, one more step. Sorry, it takes me a second to regain my thoughts. Lambda over 2 pi epsilon naught. I'll leave that out there. And then we'd have natural log of S1 divided by S. So there's another way you could write it. Because when we bring minus into a log, it brings it to the minus 1 power, right? That flips it. So then what? What happens as S goes to infinity? Well, think about this formula, right? So S1 is just like, basically the deal is we can make the voltage, we could make the voltage at S1 be 0, for instance, right? And then this formula simplifies to just, lambda over 2 pi epsilon naught natural log of S1 over S, right? So if that was the case, when you put S1 in, you get natural log of 1, which is 0, so that's consistent, right? So, but anyway, you always have the freedom to shift the voltage wherever you want. That said, we actually have equipotential cylinders here, right? So like the voltage is constant on this circle here, yeah? So these are like, voltage V of S equals to some constant, whatever. Yeah. And what happens as S increases, you get natural log of what? Natural log of something smaller and smaller and smaller. What's the natural log of 0?
It's not.
It's not. As we tend to zero, we tend to minus infinity, right? So what I'm telling you, as we go out to larger and larger circles, right, corresponding to larger and larger cylinders around the wire, our voltage is going down, 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 down. That makes sense, because what's the picture for the electric field lines here? They are orthogonal trajectories. These guys, they're perpendicular to the equal voltage surface, in this case, if you want to think three-dimensionally. And so, of course, what happens is the electric field pushes a point charge away from the line charge, right? Assuming the line charge is positive. And in so doing, it lowers the voltage. Voltage goes lower and lower and lower. There's less and less and less electric potential energy as that point charge goes further away from the line. Does this make sense? Nature always tries to, drive things to a state of lower potential energy, right? If you've got a lot of potential energy, if there's a way to use it up and convert it into something else, you'll do it. So anyway, that's that one. And again, the voltage is not zero. See this again, the voltage is not zero at infinity, right? It's in fact the voltage minus infinity at infinity. So it doesn't satisfy this constraint. What's the other infinite? So we had infinite plane charge here, infinite line charge here. Is there any other one to think about for us here? I think that might be it, as far as I can think of right offhand. Probably. More often than not, other things we talk about, they're finite in extent. So like example 3, my bad, 2. What if we had, remember we worked this example before, right? So you have Q uniformly spread for like 0 less than or equal to R less than or equal to big R, right? And we worked it out, right? We applied Gauss's law to a sphere inside the solid charge, right? And then outside. And we found that the electric field is defined as such. Well, let me just say this. The electric field is the magnitude times R hat, right? And in fact, the electric field is actually just a function of R. And what was the deal? Well, here was the deal. We had KQ, little r, divided by big R cubed for 0 less than or equal to R less than or equal to R big R. And then we just had the Coulomb field, KQ over R squared, for R greater than or equal to R, right? So for this example, since the charge is local, it's all of the charge is inside a finite region. Logically speaking, I have hope that I can write a voltage function that is 0 at infinity. All right. So what should the voltage function be here? So the basic observation is that because this is the case, we can expect that the electric field should be minus dV dr. Right? So we don't need the full awesomeness of the three-dimensional gradient. It's essentially a one-dimensional problem, even though it's three-dimensional, because it just depends on the spherical radius. So how do you calculate the voltage then? We've got the electric field from Gauss's law, right? Previous work. How do we find V? What do we got to do? Integrate. How do you integrate a case-wise defined function? So this tells me that the voltage, right, is something like the integral minus the integral of EdR, right? And so I'll do it in cases. Integrate this. We got ourselves a 1/2 KQ over big R cubed R squared. And when we integrate, we have to add a constant, let's say C1. And that's for 0 less than or equal to R less than or equal to big R. So context matters, right? Lots of these variables are constants. You don't have to integrate them, right? Just like when you're my Calculus 1 student and I say, what's ddx of pi squared? just to see what will happen. There's always somebody that tells me 2 pi. Right? Because once you know the derivative rule, you just have to do it. You just can't help yourself, you know? So that's a fun one. Another fun one is integrate cosine squared plus sine squared d theta in Calc 2. See, because you have methods to do that integral. But it's so much easier if you just do what? Cosine squared plus sine squared is 1. Yeah. I'm a troll. I just make tests.
You and your riddles 3.
Let's see here. So this one, when we integrate, oh, I forgot my minus, didn't I? Look, minus. There's a minus up in here. And then this one gives us KQ over R plus C2, right? And that would be for R greater than or equal to R. I included equality in both cases because there's another physical principle involved here, which is since there's no local concentration of charge, there's no surface charge, that means that conceptually the voltage must be continuous as we transition from the charged sphere out to empty space, okay? Which means that the limit of both formulas have to match up, which is just, you know, more easily understood is if I plug in little r equal to big R into either case, they got to match up, right? Now, what did I say? We want to do what? We want to, for the sake of specificity, let's try to make the voltage at infinity be 0, right? So, wish, you know, we wish, what's our wish? V of infinity equal to 0, just because, why not, right? I mean, you could make the voltage at infinity be 10 if you wanted to. Physics, experimentally observed physics, doesn't depend on the absolute value of the voltage. It depends on the change in voltage between events, right? Change in voltage times the charge in play gives you the potential energy change. So the actual magnitude of the voltage function is immaterial to like physical interactions. Nevertheless, we are trying to find an actual voltage function that we can all talk about and agree upon, right? Okay, so you guys tell me, what should I do to make the voltage at infinity 0? This is pretty easy, right? What do we do? As you look at these formulas, what should we choose? C1 and C2, we can make whatever we want. At least at the start of this conversation. It's actually not up for grabs once we're a little bit further. Yeah. So what should I make C2 equal to? 0. Right, so set C2 equals to 0 to get V equals to 0 as R goes to infinity, right? Hooray. Then what? Continuity. See, continuity then. Continuity at R equals to R. What's that tell us? That tells us that minus 1/2 K cubed. Did I mention it's hot in here? R squared divided by big R cubed plus C1 is equal to KQ over big R. So what does our constant have to be? Solve, right? So C1, apparently, it's got to be KQ times 1 over R plus 1/2. Oh, my bad. What did I just say? At what? Grief. If I could follow my own advice, R equals to R, which means that little r has to be equal to big R. So like this little r squared is that, right? Which then makes that term what? minus 1/2 kq over r. It has to be, right? You're adding two things, they have to have the same units. So the lengths have to, I mean, it has to dimensionally match up with this other thing, otherwise we couldn't have these terms like that. So anyway, so that's plus 1/2 at 1 over 2r is what we get, right? Or if you like, 3kq over 2r, I think. Is that right? Or did I somehow mess up the algebra? Let's see here. So if I do that, when you plug that value in for the constant here, we agree that the voltage at the surface of the sphere is kq over big R. Right? So in summary, the voltage as a function of position is equal to minus 1/2 kq over big R cubed times little r squared plus 3k. Of course, you could factor the kq business, kq over r business out, but I'm just like writing it like this just for the sake of not changing it too much from the expression above. And then outside you got yourself kq over little r. That's the Coulomb potential. And we could graph that, like we could graph the voltage, yeah? So let's do that. The graph of the voltage function. So here's my voltage. Here's R. Let's say this is big R. So the value of the voltage at, so let's see here. What's the value of the voltage at the origin? It's C1, right? This is the voltage at the origin then. So 3kq over 2r. Let's see here, so about here. 3kq over 2r, or 1.5 kq over r is there. And then it's, let's see here, so about here-ish. This is kq over r. That's the voltage at the surface, right? And what's the dependence? It's a quadratic, right? And so it's got a negative, so it's a parabola that's opening down, right? It's like half of a parabola, like that. So I believe it looks like this. And then when it gets to there, it drops into the reciprocal function, like that. See out here, it's V equals to kq over r, and over here, you've got yourself V is equal to, you know, minus 1/2 kq over r cubed times r squared plus your 3kq over 2r. So that's a graph of the voltage versus spherical radius there. Interesting. Huh. I think that makes sense. So if we think about the electric field, it's radially outward, right? And we found that the electric field was 0 at the origin, and then it increases linearly up to its maximum amount at the surface of the sphere, right? And then it's the Coulomb field outside. So in all cases, as you think about a positive test charge somehow being put in this, you know, region, the electric field is going to push it out, right? And just keeps pushing it out. And as the test charge gets pushed out, it's getting pushed to lower and lower and lower voltage regions, right? So the voltage is always lowering as the electric field pushes the charge out, which is consistent with my general story. But you see, the thing is, you can take this curve, right? And you can move it. You can shift it up and down by redefining the voltage. If I want to make the voltage 0 at the origin, I can do that, right? If I want to make the voltage 0 at the origin, what do? I simply choose C1 equal to 0. I'm free to do that. But if I do that, then the voltage at very far away is no longer 0, right? It's like minus 3kq over 2r, I think. So anyway, so that's the story. So let us go back and talk about another example. So the next example on my list of examples, and I think you can see example 2 has many other flavor options, right? Because we also worked other problems with what, like a charged shell, right? So you could try to find the voltage for one of those. Then you'd have like 3 different cases. You'd have the inside, in between, in the shell, and then outside. And you'd have to like fit all 3 of those cases together by continuity if there was no surface charge. If there's a surface charge, then there can be a jump in voltage there. Yeah.
So for the voltage equal to 0 and
Uh-huh.
you said that that would work for the example you just gave, voltage. Would it also not work for a wire charge?
Well, it depends on whether or not the wire of charge, I mean, that's what, well, that was my example 1, maybe? I erased it, but, so yeah, we found the natural.
Would it be different, though, if it was a wire versus just a just point charge in a line?
Well, that is a wire.
I mean, like,
If there was a current flowing in the wire, well, you have entered the future, my friend. That is the latter part of this course. We don't know about that yet. And then there's other things in play, like magnetic fields and Ampere's law and other considerations. But even if let's keep it in the context of electrostatics, right? Even if you had like an infinite line charge and it wasn't uniform, right? Like suppose you got more charges here and less here. As long as the charge goes on and on like that, you're not going to be able to make the voltage 0 at infinity, I don't think. Short of some miracle. We talked about the dipole before. Do you guys remember that? So if we have a charge and another charge, 2 charges, one positive, one negative, that gives us the so-called dipole field. And I'm trying to set it up like I have set up in the notes. I gotta find my way back to it. I think it was my example. Yeah, example 31. So if I put, so we'll go 2-dimensional here, just to keep things a little bit easier to kind of look at. And suppose that you put your positive charge Q at D0, and you put a negative charge, negative Q at minus D0. Which is not, well, anyway. I think if you wanted to make contact with like typical physics literature, this is probably not the right move. You probably should put one at d over 2 and the other one at d over, like minus d over 2, because a lot of times people would use d for the distance between the charges in the dipole. And so whatever we're writing down here is at odds with that nomenclature. But anyway, because if this is the case, then the distance between the charges is 2d, right? So the question then is, what's the voltage for this system, right? So it's local, right? And we can just write it down. Like, so the voltage is simply, kq over the square root of, let us say, x plus d squared plus y squared, because that's the distance to, oh, my bad. There's a minus here, right? Minus. And then plus kq over, what's the distance? I should probably include in my picture a point. Here's the point, xy, right? We're trying to find this distance and that distance, right? So I'm going to call this D1. I'll call that D2 just for the sake of discussion. So this is D1. D2 is, well, x minus d squared plus y squared. All right? And this gives us the voltage for the dipole, just like that. And obviously it's subject to the constraint that the voltage is 0 at infinity. Now if you look at page 45 of my handwritten notes, I actually calculate the partial derivatives of this monstrosity, and I show you that we get back to the electric field that we wrote down before, that we found by just vector adding the Coulomb field for both, right? But I don't know about you, but I personally think that adding scalars is much easier than adding vector fields, right? Like, here's the difference. When we work with electric fields, we're basically almost working with force, right? So electric field calculations, it's a lot like you're almost looking at F equals ma, right? We're looking with voltage, we're more in the world of like energy analysis, right? So we'll multiply by Q, then you've got the potential energy between these two charges forming the dipole and a third charge that let me call it Q3 or something, you know. Okay, anyway, so there's that. Now, if we can do 1, if we can do 2, so generally, we can say that the voltage at R, all right, is going to be the integral of K dq over script R. So, you know, instead of just adding together the Coulomb potentials like I do in example 3, if we have a continuous distribution of charge, assuming it's like localized, we can just use a superposition, just add all the voltages together. And the thing is, if all of those are subject, and it's consistent too, right? So like all of these have voltage 0 at infinity, right? So when you add together things with voltage 0 at infinity, they all also have voltage 0 at infinity. So like we're adding together voltage functions that are subject to the same boundary condition. You know, if I tried to add together voltage functions for two different charge distributions, which were based on having like the potential set up differently, I think I could get into trouble with that. But that won't happen as long as all of the charge is local. Then I just do this integral, and I've got voltage 0 at infinity. Now, how does this actually accomplished? Well, what do I mean by an integral over dq? So in terms of interpretation, this could either be a line integral, a surface integral, or a volume integral, right? Depending on whether we're talking about a one-dimensional distribution of charge, or a two-dimensional distribution of charge, or a three-dimensional distribution of charge. As far as I know, we don't do four-dimensional distributions of charge in here, so we'll stop at 3. Because no one's really found any experimental evidence of a fourth dimension yet, as far as I know, unless you think of time as a fourth dimension. But time is pretty clearly not a spatial dimension, right? It's easy enough to walk back and forth like this, right? I'm going forward, and then I'm going backwards. This is much harder to achieve in time, right? Unless you're God. So I think God's the only like legitimate time traveler. And I'm pretty sure he could if he wanted to. And I think he does. But anyway, that's another topic. So anyway, so how do we actually put this into play? It depends on the example, right? But my point to you is that this could work out like the integral of, what I'm trying to say is lambda could be dq ds, where we're talking about like arc length. Or we could have, you know, a surface charge, which would be dq dA perhaps for like an area, or we could have a density rho, which would be dq dV, right? And so depending on which kind of thing we're doing, we'd either write dq as lambda ds, or we'd write dq as sigma dA, or we'd write dq as rho dV, and we'd proceed accordingly. So let me be less vague. Like, let's work an example which actually deals with this issue. All right, if I can, I left my phone at home today. I don't know what time it is. Ooh, maybe I should use the projector. Let's do that. All right, so, oh. Wowzers. Come on, computer. You guys excited about CFA? No?
Yup.
Yep. Okay, very excited.
I'm jumping on the seat.
You're literally jumping up and down on the inside. Just on the inside. Okay. That's good. All right, so we are currently in the midst of my potential notes. And so the start of the potential notes, I derive conservation of energy, and I did things a little bit differently in here than I have in the notes, you know? Like in the notes, I just calculated the change in energy per unit, you know, the derivative of energy with respect to time directly, and went that direction to change this to like, you know, basically MA minus MA, which ends up being 0. So then, of course, the, well, that's not cool. Seriously? Okay, all right. So then, of course, the change in energy, d dt is 0, which means energy is conserved, right? Okay, so, come on. All right. So anyway, let's get past all this stuff. We've done this already. All right, we've been through this already. Did this stuff last time. Hopefully last time was a little bit of an improvement on that. So I guess the thing I should mention before I get to the integral, if I wasn't so, what's the word? All right, fine. No, I don't want to save it in my differential equations. How about downloads? There we go. Insecure download blocked. Oh, I need to. I think I don't. I haven't done that Jerome thing yet. I think that's part of my problem. Anyway, here we go. All right, so here. Sorry, guys. I'll get to it eventually. So to start with, if you have a finite collection of charge, right? As long as you're content with the voltage of the net distribution being 0 at infinity, you just add the Coulomb potentials together, and that gives you the net voltage. Simple as that, like we just did for 2 with the dipole, right? But you can do it for n. And then the thought is simply this: if you let the limit as n go to infinity, the summation becomes an integration, right? And depending on the geometry, we either interpret that summation, the infinite sum, as a line, surface, or volume integral, as appropriate. So here's the dipole example I was just talking about. Here's a picture of the actual, some of the equipotential lines for the dipole. So the field lines are these guys, right? But the, well, I don't know if I've got the, I was trying to draw equipotentials. These are equal voltage lines. Sorry, it's hard to see the contrast of black against black here, but all right. Here's the gradient of that voltage function. After some suffering, you get to this and that, and put it all together, and lo and behold, we're right back to what I wrote down by adding electric fields, just like I advertised. So I think that's comforting. I mean, it all works together, right? I'm not saying that that's the right way to find the electric field here either, right? The right way to find the electric field here, if you're going to, is simply to take the vector sum we did before. That's still the best way, but it is consistent with calculating minus the gradient of the voltage function. On the flip side, if I was to ask a question about like the motion of a third particle as it responds to the electric field of the dipole, and like how fast is it going when it goes from like point A to point B, I definitely want to use the voltage function, because that would give me an account of how much energy was, you know, coming or going from the electric fields of the two charges as they interact with a third. So here we go. So the potential, here's a question. what is the potential due to a line segment of charge? So we got a line segment of charge. I think it's uniform. So here, we got to do that pesky integration again. Let's see here. So I'm putting my charge going from 0 to L, and I've introduced AB as where I'm trying to find the voltage at AB. The reason I did that is just because I wanted to do an integral in X as opposed to doing an integral in A, which would just kind of weird you guys out. So my approach is to introduce AB as like the place I'm trying to find the voltage, work out the calculus, and then at the end of the calculation swap out AB for XY. Because ultimately I'm actually interested in what is the voltage up there at that point, right? But at the same time I want to call this X. All right, so anyway. So what's the bit of charge here? Well, it's lambda dx, which is Q over L times dx, right? We've done this before. So I have to integrate k dq over r. I'm just adding up the little bit of voltage from each, bringing in each little bit of charge to that line segment, right? You can think of it as, you know, adding the energy it takes to assemble the line charge bit by bit, building it up. And so we got k dq over r, we do this integral. To put that into practice, we're integrating from 0 to L of this k lambda dx. My r, right, the distance from here to there is x minus a squared plus b squared, because this is at y equals to 0, right? So the vertical displacement's always b. That's why I have x minus, or in this case, a minus x squared plus b squared. It's immaterial, right? Like this is the same as x minus a. When you square it, you can either do x minus a or a minus x, like whatever floats your boat, you know? So then after some calculus, which you guys know and are comfortable with, of course, because you are people who have successfully navigated the horrors of calculus 2, right? Or you're somehow not, somehow you're here and we have not kicked you out because I don't know how that happened, but it's fine, you can stay. But you're technically not supposed to be here. But anyway, these things happen. I mean, it is true we don't use calculus 2 too much in here, but definitely it's nicer to be in the midst of calc 3 in here as opposed to not, or to be done with it. Yeah. Okay, so integrating that ends up giving me a natural log of this business right here. It's not obvious. The calculus is over here. It ends up being the secant integral. Yowzers. That's a nasty one. So it ends up with the natural log of the sum of secant plus tangent, but I have to look at the triangle and make the usual substitution business there. Let me get down here. So the integration's not easy, but you can do it. And once you work through it, you get this, which then after a little bit of algebra, it cleans up this. So here you go. This is the voltage function for a line segment of charge. And then at the final finishing blow, I switch out A for X and B for Y, because I'm interested in the voltage at X comma Y, generally speaking. And there it is. And so then you can look at this formula and you can think about interesting cases, right? So like what happens if you put X equal to 0 and you let Y go to infinity? What should happen? We have charge Q distributed over a line segment. It should look like what, eventually? So it's this, which is that. And so you could put these two things together. Let's see, what do I got here? Oh, so I differentiated it with respect to Y. And if I do that, I get this, right? And then I'll continue on the next page. Basically, this whole calculation is to show you that, in fact, if we look at the long distance limit here, after some calculus, some non-trivial calculus, I suppose, we end up with minus kq over y squared, which is what we expect. It's the Coulomb field. Woohoo! I differentiated with respect to y, so that gives me the gradient in that direction. Anyway, I wanted to show you this example. Oh, check this out. I actually gave this as physics homework one time. This is the voltage What if instead of having one line segment, you had Q over 2 here and Q over 2 there? And you wanted to find the voltage due to an L of charge. This is the formula. Just doing what we did, vertically and horizontally, just by the symmetry, you can write down the formulas. And there's your voltage function. So it's kind of fun. I think this last example is at a slightly higher level than the earlier examples, yeah?
Yeah.